Unforgeable Distributed Capabilities. Here's Alan Karp, and this time I'm going to violate my rule and say a little bit of introduction. I worked for Alan for many years.
A few years.
Alan has reinvented capabilities, not knowing that that's what he was doing at the time. He came up with a paradigm that we, in retrospect, he named split capabilities. And they were very interesting, having come from it without any historical background. He reinvented them differently. And I'll just leave it at that.
Yep. And just by other way of introduction, Earth Computing Corporation has nothing to do with capabilities at all, although I will be using them in the development of it, but it's a network fabric company. First thing is, I was surprised that this title was controversial. And by way of showing my understanding of why it's controversial, I will prove that you can have no such thing. So the only way for... Huh?
I'm convinced. Good proof.
The only way I can use a capability on a remote machine is to send bits over the wire, right? And if somebody else can guess those bits, somebody else can send the same bits over the wire and get the same permission. That's not unforgeable. QED, we're done, right? All right, but let's just look a little deeper. So I'm going to start with I thought everybody would start with the definition of capability. Here's my definition of capability. A capability is a transferable, unforgeable permission to use the thing it designates. All right? I think that's a concise definition of the capability. And these words in blue, I'm going to talk about all of them, and I'm going to start with permission because we usually say authority. So let's go back. Were you the one who made the distinction, Markham?
Yes.
Yes. Markham was the first one to make this distinction. Now, I think everybody in this room probably understands it, but I'm going to give my example anyway, because for people who have never heard of the distinction, it seems to work. Okay? So it's a difference between may versus can. Permission is the rules as they are written down. In other words, I may access that file because I have the capability. You may not because you don't. That's the rules as written down. Authority is more about can. What kinds of things can happen in spite of the rules as they're written down. It has nothing to do with hacking. It has to do with the talk we heard earlier about authority. So let me give you my example. In my company, we have a server, a computer, and it's got a file on it that represents our home page. And the boss looked at the access control list, and he saw the admin can read and write the file, and the account running our web server can read it, and nobody else has any permission to it at all. Therefore, he concludes, we can put all our company secrets on that page. Well, of course, you come along, and you point your web page to our web server, and it uses its permission to read the file and its behavior to show it to you. So even though you don't have permission to read the file, you have the authority to see its contents. This is not quite right, but it's good enough to get the basic idea across to people who've never seen it. All right, so I want to start with a single program running on a single machine in a memory-safe language. And I have three objects, and it's not showing up very well here, A, B, and C. All right? And A has a reference to C, and B does not. We want to keep it that way. Okay? So when A goes to invoke C, the runtime picks up the address of C and does whatever magic is necessary to make the invocation happen. And if B happens to know the bits in the address in C, it does B no good, because there's no way for B to use those bits to get the permission of the capability. So that's unforgeable. More precisely, a capability is unforgeable if there are no bits that can be turned into its permission. That's the definition of unforgeable. I don't think there's any controversy in that. Even Dean Tribble agreed that that's a good definition. He's tough to satisfy. Okay. What if you don't know Dean Tribble? You know why. If you know Dean, you know why Markham's laughing. All right. So what about in a non-memory safe language? Well, now the mapping is held by the objects, not the runtime. So in order to invoke, A creates a pointer to this address, and the runtime does the magic to make sure the invocation happens. But if B knows the address, then B can invoke C as well. And that's what we don't want. This is not unforgeable. So what can we do? What do we call this? Well, we could use address location randomizations, and then B would have to guess the address of C, in which case we'd say the capability was not unforgeable, it was unguessable. But there are many ways that B can come to know the bits in the address. To guess it, there could be a side channel. A could be in cahoots with B and use a covert channel, or B could read it in the New York Times. That's the ultimate test for unguessability versus unforgeability. Are there bits I could put in the New York Times that you could read and it would give you the permission of the capability, right? So what are we going to call this? Well, I've made up a new term. I'm calling this knowledge grants permission, KGP. Okay? All right. So that's in a single machine. What about a distributed system? Well, in order to avoid confusion, and I'm sorry for the referees that I confused you on this point, I want to introduce a distributed system that needs no secrets, no private keys, no passwords, no authentication of any kind. And it's 3 machines on a desk. All right? And I have programmed these machines. I personally have programmed these machines. So when I plug in the wire on the left-hand port, that machine gets access to object C. And when I plug in the wire on the right-hand port, whatever machine that may be, gets access to object D. All right? That's what I've programmed. And there are many ways to make it accessible. I'm going to show the case where we use a proxy on each side to handle the converting objects to bits and bits back to objects. Okay? And when I do that, this machine at the bottom says to the machine at the left, upper left here, if you want to refer to object C when you send me the bits, here are the bits you use to designate which object you're talking about. And it does the same thing. When I talk to B, right? When B connects, it says if you want to talk about object D, use these bits to tell me you're talking about object D, right? And it creates a mapping table between the string and the address. And then when A invokes C, A gets a local capability to the proxy, so that just thinks it's C. The proxy converts everything to bits, including the designation string, sends it to the proxy here, which converts it back into an object reference, and that's how A invokes C. Lots of runtime systems do this, and the same thing for B. Great, we're in great shape. Except that if B comes to know this string, B gets to invoke C, and that's what we don't want. Now you might say, well, this is a really dumb way to do it. But this is the way we do it all the time. Every time you see a Google Docs share, every time you get a Dropbox share, right? That's what they're doing. They have one mapping table for all connections. Waterkin server does this, and I'm a great fan of the Waterkin server. But almost any time you see a cryptographically random string representing a capability, they're trying to make it unguessable, and they have to make it unguessable because they don't know which wire it came in on. Fortunately, oh, by the way, that's KGP. That's knowledge grants permission. You know this designation string, you get the permission to the object. Okay. Fortunately, we can do a better job. We just have a different mapping table for each wire. Right? Now, A can invoke C just perfectly, but if B sends this designation string, this proxy says, sorry, I don't have a mapping for it. I can't invoke it for you. This is unforgeable. This is as unforgeable as in our memory safe language case. All right, well, that's kind of a funny distributed system. It's not what we really do. We really have this situation where we cannot rely on the wire to tell us what to do on the other end, right?
Just
Yeah.
back up a slide, please. Just want to point out that the technique you're talking about is a distributed analog of the operating system concept of the C list.
That's right. It's all it is. This is the key thing I reinvented. This was. I thought I was such a genius, and then I found 1966. I was doing it in 1996. I was only 30 years behind.
I'm confused. Even with different mapping tables, why can't the proxy send the bits that would, given that it's just bits on a wire?
Yes, he's sending bits, and he says, I want to invoke the object designated by these bits. And
Yes.
And it comes to this guy, and he says, I don't have an entry in my table. I don't know what address to use.
Right, but if, let me try this again. learn the bits in the mapping table and you send them from the same machine, that's okay, I see, because you've already
Yeah,
got the
that's
permission.
right, that's right, that's right.
Well, what this is not robust to, I think, is physical access.
Physical access is a different matter.
'Cause
Okay.
I could plug.
Physical, that's why I said it's 3 machines on my desk and I'm plugging them in, okay? But,
Okay, thank
but
you.
I wanted to go through a case where we had no secrets, because that seems to confuse people, and I'm gonna go through a case that requires secrets now. Because in this situation, we obviously need secrets of some sort, right? In order to get access to C, A needs some credential. To get access to D, B needs some credential. Now, what is that credential? In E, it would be a sturdy ref. But in OAuth, it would be what's called a grant token. But in both cases, they're just bits. So what happens is C presents its credential to this machine at the bottom, and now the machine sets up the mapping table for that string, for that designation, the corresponding designation, and the same thing on this side. So now, okay. So now, what happens if B knows the bits in the credential? Well, this proxy will correctly set up a mapping table with C. So let me go back. So when A presents credential C, the mapping table for the string C gets set up, that set of bits. When B presents the credential for D, this mapping table with D as the string gets set up, right? That's fine. But now, what if B presents the credential for C? In other words, B comes to know those bits. Well, then the proxy will set up a mapping table, and B, I hate the way Keynote does this, where you go back, you can't go back one animation. Mac software drives me. I liked Mac software until I had a Mac. Anyway, B will be able to invoke C because the mapping table will have the right address in it. Sorry for the folks in the back. Maybe I should have done this upside down. Anyway, too late. Okay, so what do we call this? Well, typically our credentials are unguessable strings. Markham picked the regrettable name Swiss number. He's agreeing that it's regrettable.
Yeah, I still haven't found a good term for it,
Right.
but I hate that term.
Right. Waterkin used cryptographically unguessable strings in the fragment. OAuth bearer tokens are cryptographically unguessable. But again, that doesn't cover all the ways that B can come to know the credential. So what am I calling to call this? Now, here's where I'm stretching the word authority beyond the breaking point. But there is a difference between the credential and the capability. And the difference is such that I need a level of indirection between the credential to get the permission. That's sort of like an authority, sort of like the the web server using its permission and then showing its behavior. And so this is somewhat like that, but it's probably stretching the word too far, but I'm going to use it. So I'm going to call this pattern knowledge grants authority as opposed to knowledge grants permission. So here's our distributed system, and now as long as I can protect the credential, I don't have to protect the strings I'm sending on the wire, right? That is unforgeable. That is as unforgeable as it was in the memory safe language case, right? Now, this sounds like I'm just flapping my lips here, right? Because it doesn't really mean anything. But in fact, it is possible to protect the credential better than the string I'm sending on the wire when I invoke the capability. For example, I can use a zero-knowledge proof to prove possession of the credential. It can be run in a secure enclave, as all our devices have these days, right? There are many ways in which I can protect the credential. A very heavyweight, low bandwidth, high latency protocol to submit the credential, and then do something very efficient to use the capabilities I get. But there's another case that's interesting. Say I want to run a potentially malicious object. So what I do is I use my credential first to set up the connection. Then I clear it out of everything that's running on the machine. And then I instantiate the object, and this is where I talk about transfer. and I transfer the capability to this guy, now he can invoke C, but he's exposed to no bits that could expose the credential to B, right? So even if this guy wanted to give this guy permission, he doesn't have anything he can do it with, all right? So that's it. Knowledge grants permission, right? There are bits, that means there are bits that can be used to gain the permission of the capability. Knowledge grants authority means there are bits you can learn that you can use to convince somebody else to give you the permission, right? And a distributed capability is unforgeable if there are no KGP bits, even though there are KGA bits. That's all I have to say. So, that's questions.
Sophia?
So could you go back 2 slides, please, even if the Mac is so down? Yeah. No, a little bit more. Yes, there. First, I think that on the cloud there should be a C and a D, yeah?
No. I'm saying he has learned the credential. He has learned this string of bits, but not the
Right.
credential. So his proxy doesn't have a mapping for that string of bits.
Okay, yeah.
Okay? And he's trying to
Yes.
invoke C, but there's no mapping here.
All right. But then, so here you were talking about, we will be using we will be giving the credential to the cloud in order to then create the connection.
No, not to the
between-
cloud. It goes to the proxy on the
Alright.
other machine.
And then it creates
That's
the
right.
mapping from C to.
Yeah, that's right. In E that would be called a live
Alright.
ref, right? And if the channel breaks, the live ref goes away, right? You have to represent the sturdy ref.
Yeah, the sturdy ref is the thing that violates your
That's right.
constraints. The live ref that you bootstrap from it works with these constraints, but these constraints are only meaningful if you bootstrap into it from a system that
That's right.
already respects it.
That's right.
So what you are doing essentially is, rather than every time you have to show a string or a credential in order to do the communication, you first show the credential, and then you are given a string that you can use the next time.
In fact, first you prove that you possess the credential.
Yeah,
Okay,
That's
yeah,
all you have to do.
Yeah.
We got some more questions.
You mentioned how you can build this on top of security enclaves, and yes, I agree, people are already doing that. Microsoft is
That's
building these MapReduce systems, but maybe you have an idea how to build this. What is the minimal cryptographic or hardware primitive which you need to protect the
It depends on the
endpoint?
threat model, and it's not part of what I'm even thinking about. It's specific to each system. So I'm just trying to give you the idea that you can have unforgeable distributed capabilities.
So this is an interesting argument. Let me probe it to make sure I understand it better. You're arguing that there's a distinction between the credential and that proves that I am this machine, and
That I have,
and the bits you actually send over the network,
No,
because
no.
you can do things like
I may send the credential over the network, and then I have to protect them, and they're unguessable and all that. I'm
Right.
just simply making a distinction between the credential that gives me the capability and the capability. That's the
Right.
distinction I'm making.
Okay, so let me take that as an assumption, but and I believe it's better, but as far as it goes, but when you establish that connection that you're then going to send the capability across, setting up that connection itself involves bits on the wire.
Yeah, I said it, and I said if B knows the credential, maybe by snooping on the wire, maybe there's a side channel on the wire, maybe somebody in A's machine is in cahoots with B, any one of those ways, then yes, B gets the capability to C ultimately.
Right.
But I'm saying there's a different level of protection between the credential and the use of the capabilities themselves. I could use a 10-second setup if I needed to. I sure wouldn't want to do that every time I used a capability, right? So I'm separating the dangers. I've separated the threats.
Right, okay, but I'm not, what I'm questioning is how much does that buy you, right? Because I take the 10 seconds to set up the credential, and you can't attack that part of it very easily, because you've used different mechanisms.
Yes.
But this connection I set up is a connection that involves bits over the wire,
That's
so
right.
I can attack that just as
So,
I would have in the old world attacked the capability.
No.
directly.
What I'm assuming here is what the cryptographers call a passive attacker. He can read the bits on the wire, perhaps, but he can't inject bits on the wire. So if B wants to use the
No,
capability, wait a minute, let me finish.
They're stronger than that.
I know, but let me, okay. So if B gets to know this designation, he can't use it. There are no bits in this phase of the operation that he
Okay.
can use to get the permission. That's the
Okay,
point
so
I'm
with
trying.
the right
And
attack
yes,
model, it does make a difference.
that's right. And it is stronger, but I just wanted to be very,
Yeah.
yeah, go ahead.
Just a quick question or comment so last week I caught up with Joe Bader and he was talking about lessons he's learned from implementing Kubernetes and taking Kubernetes to a wider audience, and he was talking about the stall in the garbage collector as Kubernetes used in an enterprise. And your example here of the KGP versus KJ seems to give a good example, because as garbage collectors have been written for 3 machines on the desk, they haven't been written for distributed systems, and we get into these stalls and then the system stops responding.
Well, that's a different problem. The distributed system I wrote that used proxies did distributed garbage collection. We had no problem with that.
Okay.
But that's a side issue that depends on the details of the architecture. Kubernetes in particular looks to me a lot like a boiled frog. I mean, they had some really good ideas that worked really well, and they kept just, when they went up in scale, they applied a few additional things, and then went up in scale and they applied a few additional things. And right now, the people who are using Kubernetes are going nuts trying to manage, connections. Like this, how does this container talk to, and how do I tell them, but I've got 100,000 containers. I can no longer do it in a list. And they've got the wrong model, I think. Our company has a better model for that, but that's another story for another day. That has nothing to do with capabilities.
But does it have to do with garbage collection,
No,
distributed garbage?
no.
Okay.
All right, thank you very much.